Tuesday or fear or things like that. He doesn't have any grasp of concept there. So when we communicate with him, it's at this low level. It's like at the lowest possible instruction set that we have with him. And that's also how he expresses to us. So we need to be able to pick up these little signals that he sends to us. And we managed to do this over 19 years now, so we can actually read what he's saying, but it's really expensive. Like learning one sign for him took like 3 months, 6 months, like a long time. And it's almost like we're programming Java or C with him. It's like at that level, right? So, and people need abstractions. We need to think about higher level concepts. Like everybody here has a phone. You don't really think about how it works. Like the packages that get sent through the, how does GPS work? Like everybody can explain how GPS works, like a satellite or whatever. But when you use it, you just see a blue dot that tells you where you are. You're not constantly thinking back, like how does it actually get encrypted and all of this timing and so on. So you use the abstractions to cope in life. We do this in programming as well. We came up with the concept of design patterns because they're a much higher level way of explaining what a visitor pattern is or a factory. And if you can't express yourself in this high level, then it's really hard to have a meaningful discussion. So that's really the theme of today, abstractions and how do we get to them. So my name is Laffra. I grew up in the Netherlands. I got my master's at the Free University here, which is not free, but it's here in Amsterdam. And it's just practically free, actually, because compared to the US. And my dorm was over there, so I had to bike through Amsterdam every day on the way in and on the way back. On the way back, you go through the red light district. It's really special. But in the morning, you ride back, and there is no more red lights, but all you see is like the after effects of it, and that's really depressing. So it's like a binary thing that you go through. I did my PhD primarily to get out of military draft, and then I left the country because that was the only way to get out after my PhD. Since then, we abolished military draft. So I worked at IBM Research, a little bit on Wall Street, and then back to IBM. I ran a lab for OTI here in Amsterdam, and I basically spent 25 years in the US working on things that I like to do is programming languages, implementation, and you can see a lot of pictures there, so I like to visualize things that are happening inside a complex system, again, so that you can find these abstractions and maybe find things that are broken in the system. So I'm going to talk about a dozen or so influential and historical little languages. And then the second part of the talk is the ones I worked on, which are not influential or historical, but that I learned a lot from. So the first one is Logo. And Logo was mentioned briefly by Felina this morning. It's a very nice domain-specific language. It has abstractions of a turtle that can move around on the table, and you can go forward, you can go left. And it needs to have some kind of iteration, so you need variables, you need to remember things. So you have a syntax like make pause 20, so that means you can read this out. You don't have to fight over what it says. Like it really says make pause 20. And the while loop is also rather unambiguous. There are blocks. It looks like there's indentation which is relevant, but it's not really, so you can also have a block on one line. So it has concepts already like iteration and taking instructions together, those kind of abstractions, but that's it. So with that, you can make really interesting visualizations. This is only one of them, but you can make a fish and things like that. This is Seymour Papert, who worked also with Marvin Minsky and was mentioned this morning as well in the keynote. He designed this language for teaching children how to program. So he tried to grasp a concept that they can understand, which is that abstraction
which means a turtle can move in the direction, and that's all we do. So you start with little steps, and then, okay, make it turn around, turn around, turn around, and then you make a square. So I mentioned the word DSL. The title of the talk is Little Languages. Oh, one ahead. Hold that thought. The second DSL language I'm going to talk about, or little language I'm going to talk about, is shell programming, which I think is the most elegant DSL ever written. I mentioned I did my master's at Free University here in Amsterdam, which was with Professor Andy Tannenbaum and Dick Rune. And a lot of my education has been into how do you implement programming languages? How do you write operating systems? And how do they interact with each other? And how do you basically teach your computer how to do things? This was one assignment that we had in the computer languages class. And I still remember this one literally. I remember very little from my education at the time, but this one has really stuck. And this is like, think about this, how you pronounce it. So everybody here, I assume, has done shell programming, has written something like this with this character in the middle. So how do you pronounce this? So when you start programming, you say sort with a vertical thing, to unique with a vertical thing. But as you've done shell programming for a long time, I pronounce this as so it goes like, it's like something that flows from left to right, right? So you start pronouncing things differently. So the essence here is that you have individual things that run at the same time. They produce data, and they pass it on to somebody else. So you go from left to right here. So you sort something, then you take the unique words out of it, and then you count. And we had to implement this in 10 languages. We could pick from a palette of 20 languages that were available in that time. And there were languages like C, Pascal, I made a list here, Algol, APL, Fortran, Ada, Lisp, and assembly, and things like that. And you got one for free, which was the shell. So this really taught us as students to compare the languages. And I thought it was like a great assignment. So if anybody here is in teaching and doesn't do this yet, like, this is what you should do. Later on, we had to actually implement a shell because Andy Tannenbaum was building an operating system called Minix. And he was very smart because he used all his students to write all his code. And so he made like 500 students write a shell and then pick the best one or pick the parts of it that they liked. So we had to write a program that can read this sentence and execute it. So then you have to think about like, oh, this is really a program, and I have to start a new process. And I have to allocate ports, and I have to take the output from one and pass it on to the other. So you think about sockets, and you get introduced to things like, well, I can run them at the same time. But I can start the sort, and I can start unique, and I can start word count. And it doesn't matter how long it takes, but they just keep going. So it also introduces you to concurrent programming. So this language has been highly influential for my education. And I think it has withstood the test of time. This was in 1971. So every slide has a year date on it. And so this is, nothing has changed really in shells. This is what you use. You can also use expressions and then insert them into a call. So in this case, you could do a tail on the first file in the directory. But that is not idiomic. Like you can't like really read this from left to right, right? So there's a hack in shell which allows you to take whatever comes in from here and pass that in as arguments to the next one. And then it becomes something you can, again, read from left to right. So I mentioned DSLs. The talk is called Little Languages. So what is the difference? I've asked a couple people before this talk, like, what is a DSL? And nobody can tell me. It's like, oh, yeah, it's either external or internal, and it's an embedded or not. And I think the best definition is, like, show me a language, and I can tell you whether it's a DSL or not. but that's about it. So that's why I didn't call the talk DSL or something, but I call little languages, because that's a lot more simple. Like, a little language is small. The syntax fits on one page. The implementation is maybe a couple hundred lines, and the abstractions are high. Now, how you implement this, whether you host it on another language or whether you do it inside another language. So in a shallow embedding, this might be a library that you implement. It might be D3.js or jQuery in JavaScript, which by itself is a library. But it really becomes a language. It becomes a thing with its own abstractions and concepts that you really have to understand to be effective in it. But you don't need another IDE. You don't need a compiler and whatever. On the left side, in external DSL, you really need a compiler. So that's expensive to design. Maintenance in both is also expensive, but we'll get back to that later. And sometimes your DSL is just a way of expressing things differently, either for addressing another target or doing performance, or you have annotations in your language which change the semantics of something. In a way, you can view that as a DSL as well. So now we know the rules, what a DSL is. So Smalltalk, would that be a DSL? So I said earlier, the syntax has to fit on one page. This is the entire syntax of Smalltalk. These are all the things you can do in Smalltalk. And it gives examples of each concept. So that's simple, right? And Alan Kay said, like, when he started Smalltalk, he said, I can implement Smalltalk in a page of code. So this must be a DSL. I mean, it's so easy. But really, it's a general-purpose programming language. Don't think we would call this a DSL. We would call it a little language. And it's a perfect host for building DSLs in, because of the implementation techniques behind Smalltalk, is that everything is an object of what we usually say, but you have reflection and reification, so you can redefine basically the meaning of everything. You can change the way that methods are dispatched and invoked. So you can make awesome DSLs in Smalltalk very easily without having to write a compiler or whatever. It's just by talking to the system itself while it's running. But it's not a DSL, but it is a little language, because if you take apart the word Smalltalk, it's small talk. Small means little, and talk means language. So it's one of the first real little languages. Another DSL is Prologue. Not a lot of people have actually run with this, but we had to do that assignment that I mentioned earlier in Prologue as well. So think about how you do word count and unique and sorting in a predicate-based language where you focus more on the end result than you do on how do you solve it. So that's the main abstraction that Prologue offers. It's a logical, declarative, problem-solving language which takes you away from the how into the what. Later on, I worked at Bank of America in 2010. We actually used Prologue for authentication or authorization of people. So you can do this if you're in this group, and you can do this if you're this person, but you cannot do this. So we had all these rules defined for capabilities, and then you could ask the system, is this person allowed to do this? And it would like apply all the rules, even if they're conflicting and whatever, without us having to look up data tables and whatever. So it's a very nice way to make declarative statements about your assumptions on the world and then draw conclusions out. It's very similar to machine learning as well, where we don't focus on how do we get the answer, but we classify things based on inputs that come in and so on. Another query-based language is SQL, where we focus on the result. So you say, give me all the people where a certain attribute is valid. You don't explain how you do this. Things like indexes, or if table joins have to happen, you abstract away from that and you just say like what you like to see, and the system will do the calculation. So you get multiple implementations are possible now, and multiple optimizations are also possible. The first time I saw QBE, I thought like, wow, this is really awesome, because that takes it really a notch higher than SQL. where you give an example, a concrete example in sort of, I'm looking for a picture like this, and then Google will find it from all the millions of pictures that are there. So you lift up basically the level of communication with the system there. So my talk is called Little Languages. This is in retrospect to a talk or an article that was done by John Bentley called Programming Pearls. And he came up with these 7 rules on designing a language. So if you design your own little language, then you have to keep things that are unrelated. So that's orthogonality. If you do something in one place, you also have to do it in a similar way in the other way. So that's generality. Openness means that you can extend the system. So if no matter how interesting or powerful or abstract your DSL is, if you can't express new thoughts in it, then it's kind of useless and it will die. And things like completeness. So can you really describe all the things that you care about? And that comes down to the domain-specific part. So the DSL is often choosing a particular domain, and you need to capture that domain. If that's financial interest rates, or if that's like chemical things, or if it's insurance. But within that, you have to talk the language that your user's talking at. So how do you implement a DSL or a little language? Traditionally, you do this since 1975 around, is you take an input file, which is a list of characters, you turn it into tokens using regular expressions. Regular expressions themselves are, of course, a DSL because they're embedded in many other languages. They have their own semantics, and the ideas move between different languages. Examples are lex, flex, moo. So you get a list of tokens, and then you try to, this basically you have this parse graph, and you try, oh, maybe it's this. No, it's not that. You try another path. No. So for that, you need not regular expressions, but you need a context-free grammar. And you have rules for your operator precedence and things like that. And the end result is an AST, where we, again, apply the higher level concepts that we know about, is like visitor pattern for code generation. So without these tools, writing a parser is really hard. You can do it by hand. You can write a recursive descent parser. But it tends to get big, and it's hard to really, if you look at a grammar and you look at the if statement, that's like 3 lines, you can really think about like, oh yeah, this is an if and this is an if. But if that code is spread around in an iterative language, you really have to talk down in sort of the level that you don't want to talk about. So declarative parts are really important. So a DSL, maybe a DSL should be called declarative statement language or something, not domain specific. It's more important that it's very declarative. So make is another example without which we couldn't have built all these things. Making itself is a very simple DSL. You have a rule, you say like target hello depends on hello.o, and to make it you do this, and hello.o depends on these things. So you basically get a dependency graph where these things depend on each other, and if one of these file changes, like hello.h or whatever, you don't have to recompile the rest, but you only have to do these paths here. So you can optimize your problem solution based on all these declarative rules. Make has problems of its own. The syntax is really weird, like spaces are really important. It's hard to do things in parallel. So make has not withstood the test of time. Like I work at Uber right now, we use a system called Buck. Google has a system called Blaze, which is open source, that has Bazel. And they use a similar language, but it's a subset of Python, and it's called Skylark. And it has a model behind it that allows for much better optimizations in parallel. So this is a Dutch conference, so I have to put some Dutch quotes in it as well. So this is a presentation by Eske Dijkstra in 1972 when he accepted the Turing Award. And if you read it today, this is still true. So this is from 1972, a long time ago. Well, of course, you have to use abstraction. I didn't make up these words. These are literally from his presentation. And we have to reduce the solution space. So you have to come up with things that we can talk about in higher terms. So not about bread, but we have to be able to say that we're hungry. And so we need to raise the abstraction level. People cannot deal with lots of code. If, like, I've worked on Eclipse, and there's, like, at some point, the system I worked on is 1,600 plugins, and all of them, like, touch each other. And I was focusing on making the startup faster. And it's just phenomenal, like, how much there is that you can't deal with this. It's overwhelming. So people can only read small programs. So if we can make things more condensed, simpler, but also more meaningful and higher abstractions, we have a better chance of expressing the things that we like to do, and also debug later on. Another language mentioned by John Bentley is in his Programming Pearls talk was PIC, which is a very specific, domain-specific language for building images, in TROF, which is a typesetting program that in my time you used for writing your thesis in. It was soon replaced by LaTeX and TeX, which is, we thought was a much better way of writing documents. And this language has died. I mean, you can find it. I've actually drawn this diagram using PIC and use that, the shell script line to actually generate the picture. So this is still done today, but it's really a dead language. But you can see it talks in terms of things that you care about when you're drawing pictures. You can almost read this. So you draw a line from this to that. So you can pick the syntax. If you design your own DSL, you can pick the syntax that you think makes sense. And you can like try to lower the difference between the abstraction and where people normally think in. Another example is DOT, which is a DSL on top of PIC, which is a DSL on top of TROF, which is another. So there's like turtles all the way down. And that was Dijkstra's claim also, that you need to build the tools that matter, and you need to build increasingly higher levels of abstraction. So DOT is a very specific kind of drawing, which is graphs. So you have boxes with arrows. And again, I drew this with DOT, which I found somewhere that still works. And you can make things with graphs. And this is the similarity aspect again. So an arrow looks like an arrow in your source code. It's like really here. Today you do this in PowerPoint or Google Docs, and you just drag things out of a palette. So direct manipulation is another way of dealing with the underlying sort of abstract syntax tree that you're manipulating here. And you have to project this DSL into this concrete implementation, which may not be directly obvious, even if you look this very high level of abstraction. And then wrapping up the historical perspective, before we go to the irrelevant ones and my own, is Logo I mentioned as the first language. It was also highly inspirational for Scratch. So if you look on the left, they do the same thing. So left and right try to draw a rectangle, or actually a square. And Logo is a textual language. So you explain to the Logo system how to draw a square. You do it 4 times. You have a block, and in the block you go forward and right. There are many ways in which you can make a mistake. I mean, there's syntax errors possible. You can forget the block there. You can maybe switch around 100 and forward, or they have abbreviations as well, so you can use F for forward and R for right and things like that. In Scratch, you cannot make these mistakes. Like the blocks have shapes, and a notch you can only put it in here. And you can see the structure here. So for learning programmers, especially kids, Scratch has been extremely influential because you can forget about the syntax parts. Like, we don't care really how indentation works and square boxes, but we care more about the concept, so you can step over, even in this DSL, about the lower levels of syntax parsing and things like that. So part 2 is the languages that I wrote on. This was my thesis language in 1992. I started in 98, so that's why it says 89. And Prologue was a language which I got my PhD in the same month as Guido van Rossum did, in the same country, and we both did a programming language starting with a P. And I forever hate Guido, but I've done a lot of programming in Python, so actually he won. I admit. Okay. But Prologue is actually a much cooler language because we cared about concurrency. So we thought like every object runs in parallel with everything else. Everything is an actor. And if everything runs in parallel with everything else, what is the problem? So the problem now is communication. So how do they talk to each other? And there's going to be conflicts by definition. I mean, this is like they're all running at the same time. So how do you coordinate the communication between objects? And that's what we focused on. So this is the coordination language for a particular language. And we have these abstractions of very similar to regular expressions where you can take two paths or you can take a sequential path, which looks like shell scripts, right? And you go from left to right. Or you have optionality or you have guards, so based on a conditional. And with this, you can describe the behavior of a bank account, for instance. So one guard says, you can only withdraw money if the balance is greater than 0. And there's no test here, so there's nothing to pollute my cup. Oh, actually, there's a test here. Okay, I can remove that. Or maybe that's a different guard. Maybe I could have merged them in. Anyway, I wrote this a while ago. So is this a DSL or not? It is a little language. This is only a few hundred lines of code. It's an external language, because an external DSL, because this code here is C. We actually generated C code, and we had a runtime that was written in C. So you could call this a DSL on top of C to do concurrent programming, which was the domain it really focused on. Later on, when I moved to IBM Research, I was very interested in visualization of programs. And this is one approach I took, is you have some code on the left, and I supported two languages, Smalltalk and C++. And this is a script that describes what do you do with that state. So there's state behind all these things. So you can declare a window, you can introduce more global variables, and you can also add variables to one of these objects. So here, well, I add all these things so I can animate the state, and this thing would go up and down and would show you wrong behavior in the animation. So I have a very high-level language here. But again, you can make a lot of syntax errors. Discoverability is hard. Like, how do I know that a box exists, or text, or integer, or things like that? I didn't have an IDE, so I didn't have syntax highlighting, so learning this language was really hard. So I built a visual system that allows you to point at something and then choose something from the palette and then drop it here, and then you could say, like, add a variable. And so you could manipulate the state by symbolically executing it and then run it in real life. So sometimes the DSL is not the right way of doing things, and you have to escape to something else. This was an example where I think DSL is actually the right way of abstraction. So I worked on IBM's Java Virtual Machine team for a while, and we tried to add new languages to that environment. So I was experimenting with PHP, with C, and other languages. And we were also developing Eclipse at the same time, so I needed some IDE support, because that's assumption at that point. And I ended up writing IDEs, and that's really horrible. And you have to do repetitive stuff all the time. And I thought, like, man, maybe we can start with the grammar and then automatically generate all these extension points in Eclipse that are needed for syntax highlighting, for content assist, for folding things, and so on. So I thought, like, let's do that abstraction. That led to another DSL, a language with which you can describe languages. So it's very meta. And this has led to other work. This is now a dead project. A lot of my code is dead. But you start with a wizard. You say, create a new programming language. You give the grammar. You type in some rules. And then, phew, you get an IDE for free. I could build a C IDE in 1 day at the time. So that gives you a feeling of how fast you can do this. When I went to the CDT team and showed them this work, they were not happy because they had been working on this for months now. And I was kicked out of the building. Okay. I've shown you some insights into how you design a program. This is a programming language. This is another set of rules which were defined by Paul Graham from Y Combinator. He had this set of essays which I really liked reading when I was sort of trying to figure out what programming is. And in one of them he says, like, if you design your own language, you have to design it for people. People are going to read your code and they have to understand it. So if your language is hard to read for people, then it's really, it doesn't matter how hard it is for the computer. So think about that when you design your language. And also, if you're solving a particular problem, which is your problem, then it's a lot easier to come up with a perfect language. I noticed that when we worked on Eclipse, at the moment that we could self-host, which was about 7 months into the development, this was a huge thing. So now we could use Eclipse to develop Eclipse. And then you start to find your own problems very easily, very early. And you have to fix them because you have to use it. So if you can make the programmer the user, that's the best thing. I've also worked on other languages and other systems where we generate a language and we build IDE tooling for that, but nobody on the team actually wrote in that language. So I'll give you an example of that coming up. And there, it's really hard to come up with a high quality system because you never dog food your own tools. So if you do design your own language, find a way to use your own language in the definition of your own language. Because you will force to actually use your own stuff. And it has to be short, like fit on one page, whatever. And people have to really love it. They have to become sort of religious about that language. And they have to fight other people that are not in this language. Because that's the only way to win. And he talked about control as well. So you need to have as much control in the language as possible. I disagree with that. It's like a DSL, or domain-specific language, or little language, lifts up the abstractions, and you should hide the lower details. I should not let you go to the lower details because you might break the abstractions. And when the abstractions start leaking, then it's the beginning of the end. But that's actually a hard one. As part of the Eclipse team, I also wrote a book on Eclipse. It's actually on how to extend Eclipse. So how do you write your own plugins? So we basically iterated all the different plugins that are available. And we needed sort of a red thread to the book. So I was talking to John. I said, like, well, we should make a new language because then we can show how you implement this new language. So we came up with a new language to write plugins. So normally you do this in 7 different XML files and 2 Java files. And it's all spread out. And we try to condense that into one language. So this mixes XML syntax with Java syntax. So this is all Java. This is Java. And we figured out, we had content assist, so you can start typing like action set, and it would like know what you would have to write here, and it filled that all out. So discoverability was really good. And it knew about things like when you said message dialog, you don't have to type this thing, or you don't have to add any types because it was all inherited and invert. And we had a new syntax for creating things. I don't know why we removed the parentheses there, the brackets is like, this is breaking similarity, right? But hey, we just wrote it for the book. So EGL is another language which we developed at IBM at the time, which was for modernization. So we tried to teach COBOL programmers, RPG programmers, the modern systems that are available, and take them away from the mainframe and build Web 2.0 applications. So we came up with, this was the message. I got this picture out of a brochure that we had. This was really the message. It's like, instead of having to read 15 books, you can now read only 2 books. So that's a way of saying we have really cool abstractions, and you don't have to worry about the details. And our DSL compiled into COBOL and Java and JavaScript, so you have to worry about all these different platforms as well. So this was in 2005. In 2010, I worked on a system called Quartz, which is at Bank of America in New York. And there we wanted to take away people from spreadsheets. Like Felina said in the morning, we had too many people working in spreadsheets. Spreadsheets were literally 10,000 columns and 10,000 rows. And people wrote that, and the entire pricing strategy of the desk was embedded in the spreadsheet. And then another trader saw this and said, oh, that's great, can I get a copy? And they gave a copy to the other one. And they didn't like the cell there, so they fixed that cell. And now you get a copy of a copy and a copy and a copy. And then regulators come in and say, like, why is this number, why is this percentage this? And they couldn't explain it because you can't look inside the spreadsheet. So we said, like, can we offer them the power of spreadsheets, which is really a DAG with dependencies, so it's a functional programming language. And each node is not, like, you can recalculate, you can memorize values, you can do things in parallel, but can we give you a programming language that does that? So we used Python. So this is a piece of Python code, and it has a decorator here, like I said earlier. You can change the behavior of things. And what we did at runtime is we actually compile this again, so we get an AST out of it, and then we look at all the references to other functions. So you can see F1 depends on Y, which comes in here. It doesn't really depend on X, because the X is really an input to F2. So you basically turn around the program, rewrite it, and then run it again, implementing this behavior. And now if I change X, I can ask, like, what's F1? And you change X again, what's F1? And I don't have to recalculate this node ever. So you get the benefits of functional programming like you can do in spreadsheets. And we allowed you to save this in a database. So you could save this whole graph, this program here, in a database, and then unfreeze it with its state, and then come back. And so the iterations we did, we tweaked these values. It was a literal word that we had in the DAG. So you could say DAG.tweak X or whatever. And it would recalculate only the parts that are needed. This is a space-time trade-off because it was really hard to manage space, memory and stuff. But it was very popular. We educated like 4,000 Python developers there on the system. When I left in 2010, we had written 8 million lines of Python in the system. So you can do a lot with Python. PyAlgovis I wrote, which is coming back 2013 when I interviewed with Google. I built a website with a lot of animations of standard computer science programs. And I thought, like, it has to be easy to write them and also write the visualization. And then I basically re-implemented Hotwire that I showed earlier for showing the state in a program. So this is a sorting algorithm. Can anybody tell what kind of sorting algorithm this is? Yeah, bubble sort. Hey, you're no, you're not. Yeah, yes, you're hired. If you didn't write it, then it's okay. So the visualization can refer to the state, and I set a breakpoint on every line, and then I run this script. And there's high-level things like rect, so which is a rectangle. There's a little bit of problem with discoverability, but I only had 7 operands, so it was like easy to remember. And you can draw this, and it runs in real time. So summary and advice. If you write your own DSL, think about where you write it. You can write it as an external DSL, which means you have to write your own parser, generator, grammar. You have to write your own IDE tooling, which is expensive. And I tried to give all of these things boxes here. So if you implement your own DSL, there's a lot of work in IDE support. If you write a parser generator-based implementation, you have to write the grammar. You have to do some AST code, but if you write it by hand, that code is a little bit bigger. But if you choose a language like a host language like Smalltalk or TypeScript, at Uber, we're working on a project right now which has gone through this transition from the left to the right. So we had a recursive descent version, which spreads around the logic in different parts over pretty large files. We experimented a grammar-based one, which condensed it a lot. The whole grammar fit on one page. But then we thought, like, we can also make it a subset of TypeScript and make it an inner DSL, or internal DSL, or embedded DSL. Then we don't have to write IDE support because we get that for free. I mean, somebody else already did it, like Simon says. So we don't have to pay for that, and then your language becomes a lot easier. So if you're experimenting with a new language, start here. Start from an existing language, start building a library, and lift up your level of abstractions in that way. And maybe you don't even need a new syntax. You can build it into the same one. We implemented our restrictions in the language as lint checks and code generators that run. And TypeScript is awesome for that. It has all built-in ways of visiting the AST and do generators. They have transformers. It's a very nice platform for that. So Dijkstra, I said it earlier. These are the 3 quotes that he had in his talk again. Programming is hard. Choose the right abstractions. Use the best language. And be humble because people have small brains. And that's the end. So this is Koen, who I talked about earlier. So thank you. Any questions?
You have time for 1 or max 2. Remember the 2 rules, yeah?
Yes.
I have a short question.
There's a microphone coming.
Thank you. The statement by Alan Kay that he would be able to write a language in 1 page of code, was that before 1980 or was it after the implementation of Smalltalk? Because I own the famous books, and the book on the language and its implementation is a couple of 100 pages by Goldberg and Robson.
I've never seen an implementation of Smalltalk. There are people in the room that have, but I've never seen the actual implementation, so I can't judge if it fits on 1 page. But that's how the language started, because he believed in message passing as a language concept, and it was more a bet. He probably lost the bet, but then he won the bet as well. So it's like it always starts off like I wrote a language, and you tell somebody how easy it is to write it, and you say it's 100 lines, and then you go really count it. Oh, it's 240 lines. Okay, so we all like to lie a little bit about how hard it is to get there.
Okay, thank you.
There was one over there.
Hi, there's a lot of momentum right now about diagrammatic reasoning, which is this fancy way of doing sort of functional programming with an underlying categorical model to model stuff like quantum computing and stuff. Like, I was wondering if you had any thoughts on that, or if not, well, do you have any thoughts on that, I guess?
So there was a great talk by Eelco yesterday on SpoofX, where he basically went beyond the syntactical. And I just talked about how do you define the syntax of a language. I didn't talk at all about how do you define the semantics.
Yeah,
and reasoning about the semantics, I left as an exercise to the reader here.
Yeah, it sort of escapes that. It's just diagrams and then maths. But
yep. It's again that language that we're working on right now at Uber is coming up with the syntax is trivial. Implementing the syntax is work. But defining the semantics is much more difficult. Like the type system, we have a typing system in it. That's the hardest piece of code. And we don't even really describe the semantics on how it differs on iOS versus Android versus web, because there are differences. But yeah, there's a lot of ambiguity in implementations often. That's the hardest thing. Yeah. Okay, thank you very much.
Thank you.